Yeah. Hello, everyone. Today I will show you how to use this particle system. And this particle system is specifically designed for Blender 5.2, but using a lot of new features. And I think this system is designed pretty well. So, uh, let me help you go through the notes. First of all, here we have all this force, which is just regular force, where you can use it wherever you want. Yeah, it's just a regular vector field. And here is our particle system. Yeah, I'm using Cruiser and Bundle to split it out into different parts, and it's actually quite easy to use. Here you can see this little system, and this one is quite flexible than the old particle system where other people just group all the functionalities into one big node group, which is a little bit harder to control, and you need a lot of switch to avoid some unnecessary calculations to save the performance. But right now with the closure, we can just split the particle system into different parts. We can save a lot of performance to avoid that unnecessary calculation. So let's see. Let's first check the first field. The first one is just a point force. Point force is very simple, just attract to this point. And here we have the distance fall off. We can control if this force is scaled by this distance, which is just a particle distance towards to this origin here. So if that's 1, so that means all the particles are affected by the same amplitude, which is the same strength. If using 1 divided by d here, then this force will be scaled by the inverse of the distance, which is just the original force here. It will be multiplied by this 1 divided by d. Same for this 1 divided by the square of d here. So when the distance is get farther, and then the strength of the force will fall off. Then we have a little bit of spring force here. The spring force, let's show you. So if the points, uh, if the distance between the point and the origin is get longer than the rest length, then it will attract it to this one, attracted to this origin. If that distance is smaller than this rest length, then it will get pushed away from the origin, just like it was sticking on some surface around this origin. And the sphere surface around the origin here. And we have a little bit of hardness to control the spring force. And this vertex force, origin axis and strings 2D or 3D. So if that's 2D, it will only consider about the x and y. If that's 3D, you will also consider about the z component for the fall off here. Fall off, and we have inflow or outflow, and we have the push. We will push it towards to the center, which is the origin, and also a orbit force around the axis, so that two strings combine together here. And this is air drag force, and a mesh velocity. It will sample the mesh velocity. If your mesh is deforming or moving, then we have limit force. It just limits the amplitude of the force. For example, if the length of your force is if your length is something like 20 here, that's the length of your force, then you will limit the force length to this range. The curve force. Sample curve force here, you have the suction which will be attracted towards to the curve, and the tangential, which goes following the curve. The orbit will orbit the curve, and also reverse the curve. And line attraction will attract it to this line. Let's see. Where is it? Yeah, here is a line attraction. So attracted to these lines. So we have the line start and line end here. Also have a gravity. And this orbit force, you have the origin and axis, it will just simply orbit this here. The object force, so to say, attracted to points, edge, or face. We have strength and this fall. A cone direction, and the direction is a normalized direction. The angle fall off here is just the fall off of the angle. So for example, the co-angle is 30 here, and it will fall off here is 1. This is 0. That's the fall. Curl noise force, which is a non-curl, which is a non-divergence field. So this one can be used for some fluid simulation, which gives you a pretty nice result compared to the noise field. And this curl noise is just the turbulence here, which is being used inside of the fluid simulation to avoid the fluid loss. And then we have some B-tangent noise, which is also a non-divergence flow field, and also a sine distance field. Yeah, these two are pretty similar to the curl noise, but the calculation is a bit different. That's all. And here is a mask. It's a sphere mask to check if this one is inside the sphere or not. This one just a little visualization. The outside here of a cube. Alright, custom geometry here. Okay, that's just the force. Let's go checking this particle system. Here, first of all, we have a generated particles. That will generate the particle. So we can decide we want to use a custom point passing it into this particle bundle here. Or you want to generate some points from the surface or from the volume here. And there's just a little bit of settings for it. So density and the count method. And we have random or grid here. If that's grid, it's just controlled by the spacing between the points. If that's random, you can decide either you're going to use density or using the count. And this one just a approximate count. It's not exactly the same count, but pretty close. And then you will wire this particle bundle here into this initialized particle. And then it will convert it into a sourcing here, then later using by this particle sort. Inside here, initial particles, we have the settings for tweaking it, which is the initial velocity or the lifetime of the particle. This defines some basic attributes, properties for these particles. And the lifetime random, the radius random. And after all these settings, you can also doing some custom stage here to set some attributes to set some extra attribute you want. And then you will wire this one into this sourcing here. So let's make it simpler here. Yeah, let's see. Right now, only this particle somewhere here. Let's get around the external force. And let's get rid of the collision here. So we will see right now, this is just the simple behavior of the particle here. Because we have the initial velocity. And we can make it die in 1 second. So pretty basic behavior. So that's the sourcing of the particle solver. You will wire the sourcing bundle into this one. Then we can embody the external force here. Here we just use a simple gravity force. And we can say the particle not have the gravity, but it is not collided with this collider here. So for this force, I make it to be a bundle, just in case you want to use some information from the particle geometry here. Otherwise, it could be just a simple vector circuit instead of a closure circuit. Okay, that's the external force. After this force calculation, we also have a custom stage for this particle here. So you can insert some operations into this particle solver. Let's see. And then let's take a look at the collision behavior here. So we can wire the collision bundle here, and then it will collide with the collider here. For that one, we just need a combined bundle to combine all the collision behaviors into this bundle here. And then internally, it will evaluate all these collisions. So here is the plan one, which is just this plan. And we have a plan two, is the bottom plan here. And both of them are collider, and you wire them into a combined bundle here. So let's say some settings for it. The iteration here is just the sub-steps. So internally, it will evaluate these operations a few times using these iterations. And we have a collision detection here. Either you want to use a recast or SDF method. So there are a little bit difference here. As you can see, the SDF method will calculate the collision based on the SDF of the point. So it will be perfect, aligned with the surface without any intersection here. But with the recast here, it is being calculated using the point's velocity. So it will actually calculate the point location with the plane intersection instead of the sphere. So that will have a little bit intersection, but this one runs much faster than the SDF method. Then we have recording events. So this recording event here, you can record if this collision will trigger some event. For example, the hit and the death here. So let's wire the child particle into here so that we can better visualize it. So here, once the particle is hitting the surface, then it will trigger the event, which is both the hit and the death. If you set this one, kill particle when hit, then it will kill the particle when that the particle collide with this one, collide with this plant here. Then it will trigger the death event if you toggle this option on. Otherwise, it will only trigger the hit event. And under the particle generation here, we're using the hit surface. And if the hit surface, if your particle will last state, which is the normal component, and then if this speed is greater than some threshold, and then it will generate the particle. So here we're generating it. We record the hit event. So for this plan, it can generate some child. And similarly for the bottom plan. So here, if we set the first plan to none, which means there is no event for this plan, then it will not trigger the hit event. So there is no particles generated from the first plan. only generated from the second plan because we record the event from it here. Uh, and that's it. And you also toggle it like when kill the particle and hit here. So we can kill the particle if that one hit the bottom here. And that one will also trigger the hit and the dice event. So as we can see, hit surface or using the dice, both of them are trigger the achievement. And this one is actually a field. So if our input is a mesh, if our input is a mesh tab here, then this field will be wide down phase domain here. So you can decide which phase will kill the particle. If your input is a collection of instance, for example here, if that's instance, then this field will be instance domain to define which instance will kill the particle. And we have the fraction and the restitution here. And you can also have a custom stage here. Insert the operation after this one. After the collision calculation is been done here, you can do some custom operations. You want to set some other set of division of this one or whatever here. So this one is very flexible. This one is a surface collision. We also have a particle collision here. So the particle collision will push the particle away from each other to avoid the particle self-intersection. As we can see, we have this particle self-collision, and this one is actually depending on the downtime here. So if you make it smaller, you can say the particle collision is still pushing the particle away at the same speed because this one gives you the natural behavior. Because the dot time is very small, and here you're still pushing the particle away from each other, and it will always suddenly have a very big strings, which is a very large repulsion here to push the points away from each other and push it outside of this sphere. Because this distance is the same, so you just push this distance, but the dot time right now is very small, so that force will be very large here. So that gives you a very large velocity. Yeah, that's just the yeah. Let's push away just the same distance. Uh, so that one will give you the same force. No, that one gives you a bigger force because that based on something like internally the force will be divided by the delta t here. And then later on in the integration here, it will also multiply by delta t. Uh, that's the collision boundary here. And we have a delta time for studying the delta time globally for the particle solver here. And also a substep. So that's pretty much all. And then let's take a look at the particle attribute here. That's this five nodes, and let's take a look at the particle attribute here. So the particle attribute here we have a ID attribute, and then we have the delta time stored in the particle here. We have in particle mass. We have the particle age and the normalized age, and the left time for the particle here. and we record if this is dead or not. And here is the velocity of the particle. The velocity is uh, how much the particle moves in meters in this second. That's hit normal, hit position here, which is the when this one hit the particle or hit the surface. Then it will record the heat information. Well, the orange is just the particle rotation. Here we can see the particle are actually rotating in a pretty natural way here. When it collide itself or collide with the surface, it will have a corresponding rotation here. And we have this one, a particle or a surface. And we have a heat now, so it will record how many times it hit the surface or hit the particle, which is how many times the collision happens. It will record that. We also have an external force, which is just the force here evaluate the previous position and the slide velocity, which is the tangential velocity, the p scale, the point radius here, and the random value. There's also a position, rotation, and skew for the instance. Okay, so that's all. So the basic workflow is just here. We have some geometry and we distribute some points along on the surface here and get a particle bundle here. And then wire the particle bundle into the initialized particle here. And we get a sourcing bundle and you can wire the sourcing into the particle solver. And then here you evaluate some custom force and doing some custom stage here and then define some collision behavior using this command bundle. And you can where how many times you want. You can define these behaviors for different geometries. For example, here I'm using plan and plan 1 here. You can also set a plan 2 and define the different behaviors for the surface and it will evaluate all these closure. So after here, that's the first particle here, and we can generate some child from it. So we can make a second level particle system by using this node, which is particle children here. We have two different types. The first one is using some preset here, which is just defined in these panels. Or we can using a custom here. For the custom, we can just define some custom selection for the particle to generate it. Or this preset. So for this preset, we have a hit particle here. So if this hit particle, then it will trigger this generation. If you otherwise using the hit the surface, or if that particle is less, and then we have some threshold limitation here. So if you know limitation here, then once this collide, it will always generate it. But if the particle here, let's say, if the particle is somehow stopping here, this one, let's start the recording right here. So for example, let's find one here. For example, here this point, this one is actually stopped, but it is still triggering the generation. Let's start its last restitution here. And we can make it last a little bit longer here. So there will be the last restitution. You can see it keeps triggering the child generation because even if this point is sitting on the surface without any movement, that one is still being considered as hitting the surface. So usually we will need the normal speed here used for the threshold. So that one we're just checking the velocity in the normal component. Project this one onto this normal here, and checking this length. So if this length is greater than the threshold, then that will be marked as a valid heat surface, which is a valid collation. So as we can see, there is no particles here. Or the side speed, which is the speed to rolling, moving along the surface, which is this speed, and the normal component is this one. So that's the threshold for it, or just the total speed here. Uh, there we have the amount to define how many child it will generate. And then this again is a particle bundle, so I need initialized particle here to convert it to a sourcing model and use another particle solver here. And then again, we can define some behaviors for it, the external force, the custom state, and the collation here. And then we join them together here. And used for rendering here. So that's this one. Afterward, we have a render particle here. And this one have a lot of settings. So random particles are just instance it on the surface here, along the points. On the points, so here we have the instance, and we render it, so just as regular instance on points. We have the instance here, we have the pink instance here, instance index, and for this rotation, we can define it using the orientation attribute, which just rotate the particle accurately. Or you can just align to the velocity, so it will always align to the velocity direction here. You can have a custom rotate by here, so you can just rotate the rotation by this amount. Or just you want it to face into your cameras here, so that's your active camera, so you will see that all the particles are actually aligned to your camera view. By default, in this case, you will just using the rotation here. So that's the rotation panel. We also have a normal scale panel here. So you will normalize the instance scale. So what does this do? So internally, it will look through all the instances and scale them according to their bounding box to make sure that this instance is of a size 1. So here we can normalize it to make sure the size of this bounding box is always be normalized to 1. And this is a uniform scale, not a axis per axis component. So that will keep the shape of this one. And we have a speed by scaled by the speed. So which will scaled here. Okay. Usually you will align to the velocity. For example, we have some sparks. We have some sparkles. So we will use align to velocity and scaled by the speed. So here, like this little sparkles here, it will be skewed by this speed here. Now you can see this particle is very large because your particle radius is set very big here. So you can make it a little bit smaller, so that will be much natural here. And we can see this one here. And because they are too small, so there is no particle collider here. So that's just the default behavior. We have the initial velocity here. By default, it will act like this because there is no particle self-intersection. So once you make the radius a bit bigger, so that will trigger some particle self-collision that causes the particle to flying around. So here we can just using the cone direction so that the particle will go into every direction here. So we can better see this behavior. Let's make more restitution, less fraction here. So you can see this kind of stuff here. So it will trigger the sparkles here. Okay, that's a little bit overwhelming here. There are too many particles. Let's see. So that's it. Okay, let's just debate it after 3 seconds. So this is our behavior here. So this particle system is also running pretty fast. And we have a additional scale control for it. So that's just for the random particles. It provides you a flexible way to setting up all this rotation and scale stuff. And here we also have a curve trail here. So let me go back to orientation. Let's scale it up. So you will see that you have some curve trail here. That's kind of a challenge. So that's our curve trail for each of the points. So this one will have a default material, which is just the nice color gradient. And we have the curve lifetime here. So if you set it very short here, like 0.1, then the curve trail will be very short. You can set it to be 3 seconds, and that will be very long here, as we can see. And there's the also mass gradient here. Oh, okay. Okay, that curve is reversed. Okay, I will fix it. The left arm here and the left arm random, and we have the fading duration here. So that will control how much it will fading. So for each of the particle, as we can see, if the particle is dyed here, then the curve trail will also be dyed here. For this one, okay, that's just a reverse, which is a bit weird. Let's just reverse it here. You will see that the curve trail is disappeared very quickly, regardless of the lifetime, because the particle is dead, so the curve trail will also die here. So based on this duration, so if you decided to put 1 here, once the particle is dead, here we can see, once this particle is dead, the curve trail is fall off very quickly here. So they will disappear. But if you set it to a very long time, like 0.2 seconds, then after the particle is dead here. Okay, we also have a limitation here. So let me just set it to 0 here. The fade min and the fade max here. I will convert it to 0 to 1 here. So okay, so let's make it some mass here. Let's set it to 0. Okay. That seems also triggering it. Triggering it based on the velocity here. Okay, let's have to check this one. No matter of the lifetime fall off, I also have a velocity fall off, just in case the particle is not dead here. The particle is not dead here, but the velocity is pretty small, as we can see here. And because their velocity is too small, so their curve trail will be also very small here. Okay, that's my source of that. Let's make the lifetime a little bit longer. Let me find some particles that have a smaller velocity here. For example, this particle in here, you can see their velocity is pretty small. Their curvature very short. It seems as here. That's because this one here. Okay, let's make this one to be 1 second. This one is too long here. We will see some difference actually. We should see the difference. I forgot the setting ring here, so let's set it to 0 here. That will make some difference actually. Let's say that's too little for me. That's too 1 here because the velocity is very big. Just so let me make it something like 30. You will see the difference because the velocity is meter per second. So that one will actually very big. So usually that will about 30 here. So from 0 to 30 here, you will see the difference here. So if the velocity is small here, from 0 to 30, then it will range to 0 to 1 to scale the curve correspondingly. So if your velocity is too small here, then the curvature will be very small. But if your velocity is bigger here, then the curvature will be much bigger here. As you can see, this one curvature is smaller here, and then it will become longer because the velocity is bigger here. So you can just set it to 1 in case your particle have something pretty low here, for example 5 seconds here. So for other particles, they will have a very long trail, but for this particle who are not moving quite a lot, it will just get a very small, very short trail here, and also have a left fading. So once the particle is dead, then it will be fading out here. Okay, that's for the fading type and the curve type. And we have the render, which is the ribbon render here. We can define the shape here using just a simple plan. And you can make sure that this one will always face into the camera, or the multiply, which will have two plan so that you can see the curve true no matter which angle you're looking at. If not, if you're using a single plan, here we can see at some angles it will looking just very flat. With this multiplying, it looks much nicer. And you can also set it to be a 2 here, which uh which kind of look like a little bit stylized. And you can also use a custom profile here. For example, here we can set it using a star primitive here. Then it will have a star tree, which is pretty interesting. This one is very interesting. And for this radius, and you can use a span parameter to scale it here. So for example, here is the curve start, curve end, curve start we have a 0, curve end we have a 1. And if you have this kind of trail, well, this is a bit interesting. And facing camera, the curve tessellation here. You can see right now it's just based on the particle moment, so each frame it will have one segment here, but you can enable the tessellation to make the curve much smoother here. Okay, that's the material for here. So we have the ribbon, the final render here. So here is just a little bit of ribbon information so that we can see the ribbon will have a UV map. We have a U map and a U tail. So the Y direction here, which is the profile, it will always be 0 to 1 here. Let's see. Okay. This one have a little bit error. Fixing it in just a moment. That's the UV tile here. So the U direction, so the UV tile are based on the length of it. So the profile length is just very big. So here we can see that one just very big here. Based on the profile length and the curve length. This one will get the ratio. So Y direction will be range of 0 to 1. And the U direction will be skewed correspondingly and tell it. And we have the original curve here. So that's the curve trail. We also have a particle trail. Let's see here. We have a particle trail, for example, here from the original layer. And there we have a particle trail. We can join it in here. And we can see this little behavior. That's the settings here. Okay, that's too much. Let's lower the string. Let's lower the radius and probably lower the count here. And the dispersion is a bit too much. And we can see this is a particle trail. Here, each particle will have another particle trail. And again, control the count of the particle. And control the lifetime random, radius random, and the external force and the dispersion force. And we have a interpolation scatter, which just in case your particle, let's say, I don't know if we can keep, let's say, without the force, let's just make the initial velocity very big, for example. So you should say that these particles are moving very fast. Okay, let's still make it in a different direction. Let's scale it by 100 here. So you will see the particle moving out very fast here. And we see turbulate here. By default, it's turbulate here. Yes. The particle, I just duplicate it here. There's something wrong here. Yeah. I think that's working here. 20% by default is our dispersion, so you can say all the five particles are sitting in the same location. Otherwise, this interpolation scatter here. In theory, we should have some difference here. That's this one here. That's the particle. Okay, let's make it 24 here. Particle still seems okay on the same position here. Okay. Seems something's wrong. So the desired behavior, it should be scattered along the motion trail of the particle to get a smooth distribution so that the particle won't have these stabbing issues when the particle have a higher speed. So the particle should distribute along the motion path so that one will look continuous no matter the particle movement to avoid this stabbing artifacts. So I will double check it. That's just the settings. That's all this particle here. And we also have two groups inside the shader for providing the attribute here. That's radius, age, this some information here. So I think the design is pretty well. Yeah, I spent a long time to design the particle system, and this one is working quite well, I think. Hope you enjoy it. Hope you guys enjoy it.